Hi, everyone. It's Rachel from E1. We're opening up the lines now, so we'll give people a few minutes, well, less than a few minutes, to join before we formally start. So bear with us, please. Hello and welcome to today's live session, Evaluating Sewer Alternatives. We're covering part one today in this three-part series. So for the next hour, we will be looking at wastewater collection systems, equipment, and operations and maintenance. I'm Rachel Seiler, today's host and marketing communications manager for E1. Before we get started, just a few housekeeping notes for our attendees. All of your lines have been muted. We'll be recording today's session, and an archived edition will be available on E1's website and YouTube channel. Upon successful completion of today's webinar, you'll receive a PDF of this presentation. I know we get a lot of requests for those, as well as a certificate of attendance. And finally, we'd love to hear from you. It kind of helps make the webinar. We've allotted about 10 minutes of Q&A during today's session, so please make use of this time. And if we don't get to all your questions, we'll answer them in a follow-up email. So now, without further delay, I'd like to introduce today's speakers, both our seasoned E1 presenters, and if you've attended any of our previous webinars, you may recognize their voices. We've got Chris Nedwick here with us today. Chris is E1's National Sales Development Manager. With more than 10 years of experience in both E1 sales and field service, Chris has guided many municipalities through successful pressure sewer projects. So welcome to Chris. And today's feature presenter is Keith McHale, E1's Applications Engineering Project Manager. Keith is a professional engineer licensed in Maryland, Virginia, Connecticut, New Hampshire, with over 30 years in manufacturing and consulting engineering, focused in wastewater collection and treatment. Back in the day when he was a consulting engineer, Keith's projects involved evaluation, planning, and design of wastewater collection systems and treatment and disposal facilities. Keith, take it away.
Thank you, Rachel, and thank you all for attending. As Rachel mentioned, and as you saw from the invite, this is a three-part webinar series that will take 2 parts this week and then the last part next Tuesday. Where we'll kind of go through the evaluation of sewer system alternatives. There are many sewer system, or a few sewer system alternatives, but we're going to focus really on gravity versus low pressure. So we're going to start today kind of with the introduction of wastewater collection systems, the equipment. I'm going to touch on some of the operations and maintenance, but I'm really going to sprinkle operation and maintenance throughout all parts, because when we talk about the life cycle cost analysis in the third part, there's an operation and maintenance component associated with that. So today we'll focus really on an overview of wastewater collection systems. Part two, which is on Thursday, we're going to look at the basic system design principles of gravity sewer and low pressure sewer systems. And then next week we'll hit part three, which would be the overview of the system lifecycle cost analysis. So kind of start looking at wastewater management alternatives. And throughout the presentation, I have some slides and some discussions that kind of focus on the United States and Canada. I know there's a few people probably joining us from other parts of the world. And while I can't speak to those areas directly, the overall concepts and thoughts that would apply to what I'm talking about would really apply in your territories as well. But when we look at wastewater management alternatives, we basically have two basic kinds. You either have centralized systems, which are generally municipal systems, but they could be private, or on-site systems. Oops, we're going backwards. Now, In the United States, and these are some numbers I pulled from a couple sources, so they are going to vary a little bit. But in the United States, I found one report that says 80% of homes are connected to a centralized sewer systems. And again, most of those would be municipal systems. And then we go a little bit north of the border and we see that in Canada, according to one report I read, 87% of the households live in dwellings that are connected to municipal centralized sewer systems, and the other 13% are on private septic systems. So you can see throughout North America, the numbers vary a little, but I think when you look at kind of the population distribution between Canada and the US, we're going to have more in Canada in more urban areas, city areas. So that's maybe why the municipal systems is a little bit higher, but basically we're falling in about an 80-20%, 80% centralized sewer, 20% septic systems. And when we're looking at septic systems, like, this is a pie graph I found in a report, and it's from a Canadian system, Canadian report, but it would also apply to the US as well as other areas in terms of what an on-site system is. And there are basically 5 classes of on-site systems. You have a class 1, which is an outhouse, a gray water system. Class 3 is a cesspool. The more popular one, a class 4, which is your typical septic tank and leaching field. And then class 5 is a holding tank, where you would have a pumper truck come out and dump it when it's full. So again, this is from a study that was done in Canada that shows 78% of on-site systems are septic tanks and leaching beds. And I know from some other reports and some of my experience in the industry that 80% percentage of on-site septic systems is common for the US as well. The problem we have with on-site wastewater management is the deficiencies within the system. The on-site septic systems and leach fields have a defined, or not clearly defined, but a definite life to them, that they will eventually fail. And it's on a private lot, so when it fails, it's not always possible to put in a new leach field system. So in the United States, it is estimated that 10 to 20% of septic tanks malfunction annually. And if we look up to Canada, there's a report I read that showed 41% of septic systems in Canada have major deficiencies that impede their function and the performance of the system. So you have the wastewater going into the septic tank and then goes into the leach field, but if the leach fields have failed or the septic tanks are cracked, you're not getting the performance and the treatment that you would expect to from the on-site system. So these on-site failed septic systems, as I mentioned, do have a limited service life and a costly life cycle, that if a system fails, it is very expensive to replace it if you're able to. A lot of areas that we see in our experience where you have failed septic systems that are being replaced with a wastewater collection system, a centralized wastewater collection system, are usually around water bodies, lakes, ponds, where they're old cottages that were built on very small lots, and you don't necessarily have the real estate to expand a failed septic system. So you have these costs associated not only with the initial installation and the ability to put in a septic system based on the existing soil conditions, but you have the odor potential. In some areas, you might actually see some home site depreciation with an on-site system compared to a centralized wastewater collection system. And then, this fourth bullet I have here, it's one of those things that oftentimes goes unattended to. A septic system requires inspection, testing, maintenance, and replacement costs. Now, where I live, I have even though I work for a company that makes a product for centralized sewer systems, I have a septic system, and I have my system inspected and pumped on a regular basis. And the guy who does it always tells me that he sees me more than anybody else, and I attribute that to me being in the industry, that I know it is something that does have to be paid attention to. And when you have these problems, as I said, a lot of septic systems are on water bodies or adjacent to water bodies. So the improper design, maintenance, or location of a septic system or the private well could create problems. So these are some numbers I found from another report that showed that these deficiencies from on-site wastewater management contributed to 67% of reported outbreaks of groundwater contamination from 1971 to 2008. And these are numbers from a study that was done in the US. And then one of the problems we always see basically everywhere is when you have these failing septic systems, they can cause dangerous levels of algae blooms in the adjacent water bodies. And as I said, one of the areas we see a big problem with septic systems failing is on water bodies because of the algae bloom. Now, if you live in an area where you have a lot of space around and your septic system is failing, it's like anything. If you don't see it failing, you don't know it's a problem. But when you have failing septic systems on water bodies or adjacent to water bodies, rather, you start to see those algae blooms because the system is not operating properly. It is not removing the nutrients from the wastewater, and those nutrients are getting into the lake or the pond or even the ocean or the Gulf, and that creates some significant problems. So that's, when we look at on-site systems, and that's the problem we see with on-site systems. Now we look at centralized sewer systems. And we have two primary categories of centralized sewer systems. These are either going to be combined sewer systems or separate sewer systems. A combined sewer system is one that incorporates both the sanitary and the stormwater within the area that are collected within the same system. You'll see these, you won't see any recently, but the ones that are in place, you'll see around some urban areas, particularly the urban areas of Canada surrounding the Great Lakes, or the US surrounding the Great Lakes, and other large metropolitan areas like Boston and New York and Philadelphia, where you have those old cities that when they started to develop their centralized sewer system, it was just cheaper and perceived to be better to send it all through one pipe. So that when you have the wastewater that is on a dry weather day, just the wastewater goes through the pipe and then goes ultimately onto the wastewater treatment plant. But when you have wet weather and you have those rain events, the stormwater goes into that combined sewer system as well. And the combination of the stormwater and the wastewater usually exceeds the treatment plant. So there is what's known as a CSO, or a combined sewer overflow, where the combined wastewater discharges to a water body. In some cases, it might have some level of primary treatment, but oftentimes it's just a straight flow into the system. Now, the upside of that is it is diluted because it is mostly wet weather flow, stormwater flow, but it is a problem. So you don't see any really combined systems now in development. There are still many in existence that have to be addressed. On separate sewer systems, you have your sanitary sewer in one pipe going to the wastewater treatment plant, and your stormwater sewer in another pipe that would discharge to an outfall. And because it's only wet weather, it may not have any treatment, but in many cases, it might have at least the bare minimum of primary treatment for the stormwater flow. So now I want to kind of focus or turn our attention to the separate sewer system alternatives, or alternatives for separate sewer systems. And one of the reasons I'll telegraph what I'm going to talk about a little bit, but one of the reasons I want to really talk about the combined sewer systems is when we look at pressure sewer systems, the development of pressure sewer systems came out of, or the growth came from, the desire to get rid of the problems that are associated with combined sewer systems. But focusing now just on the separate sewer systems, you really have four dominant types of separate wastewater collection systems. And there's your conventional gravity sewer system, your pressure sewers with grinder pumps, a system known as septic tank effluent gravity or septic tank effluent pumps. And these are systems where you have a septic tank on each property. The wastewater, the primary solids are settled out at that septic tanks, and only the effluent goes downstream for treatment. And that effluent would either flow by gravity in case of in the stag experience, or by a pump. It would be discharged to the treatment facility using a pump, as in the case of a step system. And then the fourth alternative you would have would be vacuum sewers. And that's where you have a pit located on each property, a centralized, at least one centralized vacuum pit that creates a vacuum within the system and basically sucks the wastewater from the property to the vacuum station and then discharges ultimately to the wastewater treatment facility. So when we look at the wastewater collection systems, and here are some numbers from the US, and these are from an EPA report from 2009, 2010, So, that is about 10 years old from these reports, and the analysis is probably done a little bit before this, but just gives you an idea of when we're looking at the different types of wastewater collection systems, what we'll see. And again, this is the US sewer network. We would expect to see very similar breakdown in other territories as well. But in the US, there are approximately 16,000 sewer systems incorporating 800,000 miles of sewer. Of that 800,000 miles of sewer, gravity network accounts for approximately 740,000 miles. So clearly the vast majority of sewer systems within the US is gravity sewer systems. The remaining length of this, the 60,000 miles, would be attributed to pump station force mains or alternative sewer systems such as grinder pump, pressure sewer, step systems, or vacuum sewers. Also, as part of the centralized sewer system network, you have service laterals. This is the pipe that takes the flow from the house to the main sewer pipe. And there is estimated to be approximately 500,000 miles of service laterals, or in some areas called side sewers, just on the property alone. So you can see that, the on-property component of a traditional wastewater collection system is almost half of the total pipe within the system. So, the on-property stuff is a significant component of the wastewater collection system. So when we're looking at the considerations, considerations for wastewater collection systems, there are a couple real key drivers. One would be the expansion of an existing service area. Another driver in terms of wastewater collection would be a new development. Residential, commercial, you just want to develop a new area that is currently served by on-property systems, or you're developing a greenfield development with a whole new system. And then the third reason that one might consider a wastewater collection system would be deficiencies within their existing wastewater management system. So this would be, failed septic systems, which I discussed earlier, or failed gravity sewer systems, where there is an existing gravity sewer system, but the gravity sewer system is failing. So there is a driver to replace that or repair that failed gravity sewer system with another system. And when we look at those deficiencies with wastewater collection system, there's a couple of different reports. In the US, every year or every 4 years, the American Society of Civil Engineers puts out a report card for the infrastructure throughout the country. And on the 2017 report card, it gave the wastewater systems a D+. Now, I guess the good news about that grade is on the 2013 report card, wastewater systems was D. So it improved a little, but it's still a D+. And this grade indicates that the sewer systems are in fair to poor condition. It is graded as being considered below acceptable standards. One of the problems we have in the buried infrastructure world is the sewer pipes are buried. If anyone has read the ASCE reports or looked at some of the data, or even if you see on, every 4 years when this report comes out, there's always news stories about it. And the news stories always tend to focus on the bridges, roads, the stuff that everybody sees, even though in many cases, the grade for bridges is actually better than the grade for wastewater systems, but nobody sees the wastewater systems, so it doesn't get the front page. But the D+ is not really a good grade, and it shows that there is a problem with existing wastewater infrastructure within the US. When these systems fail, you get extraneous flows that overload the wastewater collection and treatment systems. So now we want to look up in Canada, and Canada did their last infrastructure report card in 2019. So from what I was able to read, it seems Canada goes more like a pass-fail type concept where they don't actually assign a grade, but they did break down some conditions and ratings on their linear wastewater assets. And they showed that 57% was considered in good or very good condition, 17% in fair condition, and 11% poor or very poor condition. 15% of the system, the condition was unknown. So what we see through these two evaluations is there is a concern in general within the US and Canada, throughout all of North America, with buried infrastructure that is not in good condition. In Canada, the good or very good is higher than what we've seen in the US. I haven't seen anything that really kind of explains the differential. It might just be some of them are newer systems up there, or maybe they are a bit more proactive in their maintenance. But no matter how you look at it, it does show that there is a problem with wastewater management or wastewater collection system deficiencies. And these deficiencies are failed gravity sewers. So over time, the integrity of sewer systems develop deficiencies. There's one truism on gravity sewer systems is it's going to leak. You're going to get extraneous flows, groundwater infiltration, stormwater inflow. You're going to get that clean water that enters the system. The unknown is, when is it going to fail and how bad is the failure going to be? Is it going to be a lot of flow that really overloads and stresses the wastewater collection and treatment systems? Or is it going to be a little bit of flow that adds cost because you still have to transport and treat any water that enters the system? So we know that, you get cracks over time. Infiltration, groundwater can seep into these cracks. And this infiltration can either be storm-induced or rain-derived infiltration or groundwater infiltration. So if the groundwater table is above the gravity sewer pipe normally, that's going to be a constant flow of groundwater into those cracks and those deficiencies in the sewer. If it's not, and then you just get the rain-derived infiltration, that's when you get the rainwater that seeps into the ground and then ultimately makes it into the sewer system. And then inflow is rainwater that enters the system more directly. These would be sump pumps in basement that are discharging into a sewer system, roof leaders from the downspouts that discharge into it, or even crossovers, known or unknown, from stormwater systems that are directly connected to a sanitary sewer system. As I said, these deficiencies within the system, we know it's going to happen. We just don't know when it's going to happen or how bad it's going to be. But ultimately, failed gravity sewer deficiencies lead to failure. That failure could involve wastewater backing up into a basement, groundwater or the groundwater entering the system undermines sewer pipes, causes road collapses because the soil was washed away, or you have the overflow going into large bodies where it's polluting the large water bodies. So your recreation, your ability, and a lot of these water bodies are actually your drinking water as well. That can create problems. So we never really know exactly how bad it's going to be. But what's important to understand is that these extraneous flows, that infiltration and inflow, doesn't have to be catastrophic to be detrimental. Any flow can be harmful to the community. Again, the problem we have with wastewater collection systems is we bury our best work. So we might have a problem with the wastewater collection system with a lot of infiltration and inflow getting into the system, but it's not really noticed until you see that high flows at the treatment plant, which that just means you're going to spend a little bit more money to treat that wastewater. But then it can get detrimental in the fact that you could have sanitary sewer overflows, and that could be sanitary sewer or wastewater coming out of the sanitary sewer through manholes, through lift stations, or backing up into a basement. Definitely, no matter where that wastewater comes out of, it's not a good thing. Another problem you have with infiltration and inflow is it does reduce the collection and treatment capacity. So if you have a system that has a lot of a gravity sewer system that has a lot of infiltration and inflow, the ability of the community to expand the collection system, which the expansion of the collection system can be easily equated to expanding of the tax base, it reduces their ability to expand that system. So many cases where you see communities that have failed gravity sewers, there'll be a moratorium on hooking up to the wastewater collection in the treatment facility. And then, as I mentioned, even if you don't have wastewater flowing out of the manholes or into a basement, and you don't have that reduced collection capacity there, or you're not really looking to expand the service area, so you don't care about that reduced collection capacity, there is a cost with transporting and treating that groundwater and that rainwater that gets into the system. So anything that enters the system has to be transported. So you have to pump that wastewater, you have to treat that wastewater, you have to discharge it, and that comes at a cost. So when we see this failed linear wastewater, our collection systems, we take this approach of sewer renewal. And these are progressive actions to return the functionality of the failed wastewater collection systems. Now here, this is kind of the quick overview. I think you might be able to find some of this in more detail on our web YouTube channel, where I go into a lot more detail on sewer renewal. But here we're just kind of give you the overview. You have three components. You have the repair, the rehabilitation, and replacement. So the first step or not necessarily the first step, but one of the things that you look at on a failed gravity sewer system is the repair. This is when you have an emergency situation, so you got to get in there, repair the pipe quickly. Then you get your rehabilitation. So this is where you have a failed gravity sewer system, but you're going to rehabilitate it using typically fold-in form or slip lining, where you use the existing gravity sewer system as the host pipe, and then you put the new pipe within the host pipe, and that it helps with the structural integrity of the system, but it definitely improves the ability to convey the wastewater, and you can also reduce the infiltration and inflow getting in there. And then we'll look at, the ultimate renewal aspect is with the failed gravity sewer system is to replace that gravity sewer system with another system. So here you have a failed gravity sewer system. You're going to dig up the street and you're going to put in a new gravity sewer system in this example. And that could be either done with a brand new system or using some pipe bursting technologies where you send a cutter through the existing pipe, burst the pipe, and then install a new pipe in its place, trailing behind it. So again, I'm just going over quickly on these alternatives. You can find more information in one of our other webinars we did that goes in a lot more detail. But you can see when you're looking at renewal, you go through the repair, which is just the Band-Aid approach. And then you start to compare the rehabilitation versus the replacement. Rehabilitation of failed gravity sewers has really got a stronghold because this sewer replacement of replacing a failed gravity sewer with another gravity sewer system creates problems in terms of what you're digging up. So the alternative to that, the better sewer replacement solution, is looking at an alternative wastewater collection system, such as a grinder pump pressure sewer system that uses a small diameter pipe, and that pipe is installed just below grade, just below, follows the contours of the land, installed just below grade. It can be installed with horizontal directional drilling methods, or what we term low impact cut and cover. So with the gravity sewer system that's going to be buried deep, if you replace that failed gravity sewer system with another gravity sewer system, you're looking at putting in an 8-inch, 200-millimeter pipe compared to a pressure sewer system where you can replace the failed gravity sewer system with a 2-inch, typically 2 to 4-inch pipes. So that's about 50 to 100 millimeters. That smaller diameter pipe that can be installed just below the frost line. So you're actually able to install the pressure sewer system while keeping the failed gravity sewer system in operation. So now looking at those two alternatives, and again, during this webinar series, I'm only going to focus on the collection gravity sewers and gravity sewers and pressure sewer systems with grinder pumps. So conventional gravity sewer are designed to take advantage of gravity as the prime driver. The wastewater flows from point A to point B under the force of gravity. The design and installation is dependent on maintaining a constant downward slope so that acceptable flow velocities are maintained. You want to maintain a velocity high enough to keep material suspended, but not too high that it creates erosion or other concerns, water hammer problems within the system. If the topography of the area is flat, the sewer pipeline is installed at an increase in depth. As that trench excavation gets deeper to install that pipe, it becomes either unsafe or uneconomical to continue. At that point in the gravity sewer system, a lift station would typically be required. And then you would lift the wastewater up and either discharge it under the force of that lift station pump through a force main to the treatment facility, or just lift it up and let it flow downhill again to the next low point. So you have the wastewater that constantly flows downhill until it becomes too expensive or too unsafe. So, gravity sewers have been around for a long time. Pretty well-known system consists of sewer pipe, manholes, lift station, and other appurtenances. As I mentioned, the sewer mains are installed at a constant downward slope, and generally the depth is going to be greater than about 6 feet or 2 meters. And as you go down, it's not uncommon to see gravity sewer depths approaching greater than 15 feet. At about 20 feet, or even a little bit less than 20 feet, then it becomes pretty uneconomical and definitely unsafe to continue installing it. So as I said, with the systems you have, with the gravity sewer, you have the sewer pipe. And you get different types of sewer pipes in the gravity sewer system. You got your service lateral, which is the pipe that goes from the house to the mainline sewer. So that pipe's typically going to be about a 4-inch. Then you get your mainline branch sewer that is most of the wastewater collection system, and that's going to collect the wastewater from the individual houses, and that will ultimately discharge into a manhole. And then typically what you might see in many gravity sewer systems, going from the manhole, you would go to an interceptor or truck sewer. So your mainline pipe is going to typically be about 8-inch or 200 millimeters. Your interceptor or your trunk sewer is going to be larger. And that's going to take flows from a sub-basin and then move it down towards either a lift station or to the wastewater collection system. So you have different pipes, again, varied at a constant or installed at a constant slope to maintain the proper velocity. And the other big component that you have within gravity sewer system is the manholes that are going to be located every place you have a bend or at a certain distance, which is often required by regulations. Then the wastewater, in many cases on a gravity sewer system, will go to a lift station. And from the lift station, it will go to a force main to convey maybe to another lift station, or in most cases to the wastewater treatment plant. And the lift stations are going to vary greatly in terms of how big they are, what kind of pumps are installed, what kind of other equipment is installed. A lot of it's going to depend on the system. So you got some small stations that really aren't much of an eyesore, and you might drive by one and not even notice it because it's a submersible system all buried. And you have larger systems that will take care of the contribution from the entire wastewater collection system that are going to be bigger stations. So you have, the maintenance of maintaining these, observing these, the power required on that. So those are the real big components that we have with the gravity sewer system. Now, in part 2 of the webinar, I'll go into a little bit more detail as we look at the design of the systems of some of these gravity components, as well as the pressure sewer components. So then we look at, advantages, disadvantages. With the conventional gravity sewer system, it's a simple, reliable operation. The most complicated thing with the gravity sewer system is the lift station. But once you have it in there, you have a pipe that flows by gravity. So it doesn't require a lot of operation, but it does require maintenance. You do have to make sure that pipe is cleaned and televised on a regular basis. But generally, very simple, reliable operation. The procedures for designing a gravity sewer are very well established. Disadvantages with the gravity sewer system: high capital construction cost. When we look at the third part of the webinar series next week, when we talk about life cycle costs, I'll show you some graphs that show, or some data that shows, that a gravity sewer system can in many cases be twice the cost of a pressure sewer system. So it has a very high capital construction cost. Less flexibility for future extensions. You're going to start at a high point, and it's hard to connect to the extreme ends of a wastewater gravity sewer system by expanding it. So you're probably going to have a lift station just to expand the system. The pipeline does have to be laid on a precise grade. And as I mentioned many times, lift stations in many cases may be necessary. It's very unusual unless you have very hilly terrain and everything is flowing in a bowl down to the wastewater treatment plant. You're probably going to have lift stations to get the wastewater from the property to the wastewater treatment plant. As I mentioned also, with gravity sewer systems, you have infiltration and inflow. This is extraneous flow that is going to enter the system. It's just a matter of when. Now we look at pressure sewer systems with grinder pumps. A pressure sewer system is a wastewater collection system that has individual residential pumps that grind the wastewater and convey it to the central treatment system, a lift station, or could even convey it to a wastewater gravity sewer system, an existing gravity sewer system. Very simple system that consists of an individual grinder pump located at each property and small diameter pressure pipe buried just below the frost line. And again, as I mentioned earlier, that pipe is typically going to be about 2 to 4 inches throughout the system. I looked at some historic designs, look at a larger data set of low pressure sewer collection systems. And these are systems that were E1 systems or systems that were done by other manufacturers, and found that basically 94% of all pipe within a a pressure sewer system was 4-inch diameter or less. So the advantages of a pressure sewer system with grinder pumps: small diameter pipes, shallow installation. This yields a much lower capital construction cost. Because you don't have to worry about that constant grade and maintain that constant grade, and you can install the pipe following the contours of the land. Pressure sewer system pipes can be installed using trenchless methods. There is what is termed a lower social cost. And that social cost, again, this is something I'll go into more detail on part 3 of the webinar series, but the social cost is the disturbance to the community. It's not a real economic cost, but it's businesses being shut down or homeowners have to drive around because of the construction that is going on. That social impact to the community. Also has a smaller environmental disturbance envelope. Another key advantage with the pressure sewer systems is it does not have any critical central infrastructure. So you'll have a grinder pump located at each property, but if one grinder pump fails, it will not impact the rest of the system. And in the case of an E1 system, it's very easy to get in there, pull that pump, replace it with a spare pump, get that system online. But even when that pump is down at that individual property, every other pump in the system would operate without even knowing that there's something wrong at one location. And one key advantage, there's no stormwater infiltration. So this significantly reduces the burden of downstream infrastructure. If you were to look at a system that was 100% gravity sewer versus 100% pressure sewer, you could actually design or hopefully justify the design of a wastewater treatment system that is smaller, because you don't have to design for that wastewater, groundwater, or stormwater. Now, I say you can design, but the reality is there are codes, so it might take a little bit of work trying to get the regulatory agency to accept that there is no infiltration, but it is definitely an advantage that you can, those downstream structures, any treatment systems could be smaller, also has a lower operating cost at the treatment plant. Disadvantages with the grinder pump systems, it's kind of hard to say as a grinder pump manufacturer, but yeah, it is. There's always a plus and minus with everything. So what could be perceived as some disadvantages, each building in the system is going to require a grinder pump unit. Now this, not a big disadvantage because it's only a 1 horsepower, in the case of an E1 system, it's only a 1 horsepower low maintenance pump. So you are going to have it located at each property, but it's not going to be a big obstruction. You do need spare parts that have to be readily available. Again, an advantage with an E1 system is there's only 1 pump. So the pump that you would have at one property would be the same pump you would have at another property. Compare that with a centrifugal system where you might have different size pumps or different manufacturers, then you got to have even more parts available. The same actually could be said for a gravity sewer system, that if you have lift stations within your gravity sewer system, you got to make sure you have spare parts readily available for those as well. Each pump within a pressure sewer system is dependent on the acceptable electrical service. Generally not a big issue, but when we look at some more rural areas, that is something that might have to be addressed during the evaluation and design phase. And if we talk about what would be the biggest disadvantage of a pressure sewer system is it's a newer application. So a lot of engineers and municipalities are not as familiar to the design and operations of the systems. And if someone is not really familiar with it, there's a tendency to just avoid it. We're going to go with, in general, we're going to go with what we're comfortable with. So real quick on some history, going back to the discussion on combined sewer systems and separate sewer systems. The evolution of pressure sewer systems started back in 1967 when there were some problems with the combined sewer systems being overburdened. So under the direction of the Federal Water Pollution Control Administration, which is for all intents and purposes, the US EPA, and the American Society of Civil Engineers, they initiated a study to evaluate options for separating the wastewater from the stormwater in combined systems. Harvard professor Dr. Fair came up with this concept of a pipe within a pipe, where you would have a small pipe located within the existing larger diameter combined sewer system, where the smaller diameter pipe would convey just the wastewater, and the conventional wastewater, and then the larger diameter combined sewer system would then have the capacity to transport just the stormwater flow. So the ASCE embraced this concept, and they set out to establish the criteria for the appliance necessary to accomplish the task of separating the sanitary sewer from the combined system. They worked with General Electric at the time to develop this new household appliance. And the General Electric team concluded that a progressive cavity semi-positive displacement pump was best suited for the application. And what was kind of nice about this process is the General Electric team was a group of engineers who were in the appliance business. They weren't a pump company that were trying to figure out how do we make our pump work for this application. They sat down with a whiteboard process and said, okay, we got this blank palette. What do we need to develop to make this concept work? And that's where they came up with that conclusion of the semi-pod displacement grinder pump. Because with a pressure sewer system, you have pumps working throughout the system, many pumps throughout the system. So in about 1969, the General Electric design team went on and founded the Environment One Corporation. So the concept of pressure sewer systems are pretty much as old as Environment One is. Environment One more or less established the proof of concept, and as with any good product or any good concept, other manufacturers soon followed. So pressure sewer system really gained its popularity with the ability to provide central sewer service in areas where it was impossible to do so before. And those would be areas that were flat, wet, rocky, or hilly. And these areas that generally was just too cost prohibitive to install a gravity sewer system. So it became the alternative when there was no alternative. But then over the years, the experience and the demonstrated advantages have expanded the use of pressure sewer systems. It is now seen as not the alternative solution, but a competitive alternative, or what we would like to call the appropriate solution when looking at conventional gravity sewer system. And a lot of these drivers are the lower environmental impact and social costs, the increased construction schedule. You could install more pipe with the low pressure sewer system than you can with the gravity sewer system. It has better construction phasing and flexibility. So you can install just the main line without addressing the homeowner component at that point. So you're able to phase the system better and adapt quicker. And it also, as I mentioned, has a lower capital construction cost. Now, the heart of the system is, regardless of the manufacturer, you're going to have a pump basin, pumps, which can be either progressive cavity or centrifugal, liquid level sensors, something to tell the pump to turn on and off, and then the pump controls that actually turn the pump on and off, and then a pump removal guidance. So that's either going to be, in the case of an E1 system, a funnel where the core just sits in that funnel, or with other manufacturers, you might see the more traditional guide rail system that does have some concerns and some problems that you want to make sure you look at. So my pacing's a little off, so I got to pick up. So the grinder pump with a pressure sewer system located in the yard or basement of each home. Wastewater flows from the household to the basin from the service lateral. The basin contains the grinder pump with integral level controls. So the pump is activated when the wastewater in the tank gets to the level to turn the pump on. It's a pressure switch with the E1 system. So once it hits that on level, it turns the pump on. The wastewater grinds, or rather the pump grinds the material, and then it discharges. And once the water level in the tank goes down, reaches the off level, turns the pump off. So the runtime is very short. Power consumption is low. The E1 system is a 1 horsepower pump, and generally the pump will operate for no more than 20, maybe 30 minutes a day. The E1 system would discharge around, let's say, 10 gallons per minute. And if we look at some traditional guidance for wastewater, homeowner wastewater generation of 200 gallons per day, that shows that we're only going to run for less than half an hour each day. So power consumption, which means power cost, is very low. So as I said, the pump grinds up the material into small particles and then discharges through a 1.25 or 30 millimeter service lateral to the main pressure sewer pipeline. Within the pressure sewer system, you could have 2 types of grinder pumps. This is going to be more of a consideration on Thursday's webinar when we talk about some of the design considerations of designing a pressure sewer system using a centrifugal or progressive cavity pump. So I mentioned, the concept of pressure sewer systems was developed by the blank whiteboard by the General Electric engineers who came up with the concept of the progressive cavity. And then other centrifugal pump manufacturers said, hey, we can make that work as well. So when we look at the pumps, the centrifugal pump has that rotating impeller that imparts the rotational energy on the pumped fluid. It is greatly affected by the system pressure. And that's a big consideration when you're looking at pressure sewer systems is, if we look at a typical house, a typical system, let's say 200 homes. These pumps are going to turn on and off at different times throughout the day. They're going to operate for less than 45 seconds each time. So when you have that pump comes on, you're going to have your system pressure change, either go up or go down. And that's going to impact how the centrifugal pump operates. Then we look at the progressive cavity pump. So this is a semi-positive displacement pump where you have a stainless steel helic rotor and stationary elastomer stator. The wastewater is ground up, and then the rotation of the rotor within the stator creates a series of cavities that conveys the fluid through the rotor and then through the pipe. So it's a plug flow operation. It produces a constant flow rate and is only marginally affected by the system pressure. So this is just the illustration. So you can see with the progressive cavity pump being a plug flow system, regardless of what the total operating pressure is, and that's the, the y-axis on the graph to the right, you're not going to have as big a discharge. It's generally going to discharge somewhere between 8 to 12 gallons per minute, generally around 10 or 11 gallons per minute. So you're going to have pressure changes, but the discharge of the E1 grinder pump, the semi-positive displacement pump, is not going to change that drastically. And we can really see that when we look at, the overlay of a centrifugal pump curve, which is curve A, and a progressive cavity, which is curve B. So, I mentioned that, when you have a pressure sewer system, you have many pumps that are operating on and off very quickly. That's going to give you a very dynamic system curve. The total hydraulic head within the system, the wastewater collection system, is going to change depending on how many pumps are discharging into the system. So one of the ways we like to look at it is when you look at these two curves on the right-hand side of this graphic, the horizontal lines, you can see 1, 2, 3 going up to 9. That's the number of pumps that are operating. And, I mentioned the total operation of a pump is only going to be about 20 minutes per day. And each time a pump turns on, it's only going to operate for less than 45 seconds, plus or minus. So you might have, start off with 1 or 2 pumps operating, and that's going to be on the low end of your total dynamic head. And then the pump might come on, so now you got 5 pumps operating. That's going to increase your total dynamic head. But shortly after that, 1 pump turns off. So you're always going to be changing your total dynamic head within the system. And you can see when you look at these curves, as your total dynamic head goes up or subsequently goes down, on the semi-positive displacement pump, you're only moving up and down that near vertical curve. So the discharge is going to be pretty consistent, pretty constant. Compare that to the curve A, which is a typical centrifugal pump. You're going to be moving on the large range of that pump. So on this illustration, what I would call the best efficiency point for a centrifugal curve would be about 7 pumps operating at the same time. And this is just illustrative purposes, but that's generally where you would see it, the middle of the curve. But as you have more pumps come on or more pumps turn off, that centrifugal pump is either going to move to the right-hand side of the curve, where it's in the cavitation zone, or it might move up to the left-hand side of the pump curve, on the centrifugal pump curve, where it's going to be deadheading and be in a recirculation zone. So that creates a lot of stress on the pump. And that's something I'm going to go back to this slide on Thursday when we talk about the design, because when you design a system, this becomes sort of the critical component. So when we look at systems, and I'm not going to necessarily hit every point on this, but when we're doing that evaluation, this, the first webinar is just kind of the introduction, the overview, what is the difference between a conventional gravity sewer system and a pressure sewer system. Some of the things you want to look at, with the infiltration and inflow, that is included in the design. It is going to happen with a conventional gravity sewer. With pressure sewer systems, that infiltration and inflow is avoided. Gravity sewer systems, you got to make sure you maintain that minimum velocity to avoid solid separation. So you're going to have a minimum pipe diameter of 8 inches, and it's going to be laid at a constant slope at all times, so you maintain the proper velocity. Velocities are a consideration for pressure sewer systems, but they're less of a factor. And in the case of a semi-positive displacement pump, they become even less of a factor because the characteristics of the semi-positive displacement pump creates what we call a self-cleansing velocity, that if you do have solids deposit, solids settle out, they'll eventually get pushed down there, because when you have that increased resistance, it's just going to push it there. It's not going to move to the right-hand side of the centrifugal pump curve. Trench depth, with a gravity sewer system can exceed 20 to 30 feet. You're generally not going to see a gravity sewer anything greater than 20 feet because it does become a heck of a health issue. With pressure sewer systems, you have minimum trench depth buried just below the frost line, and the depth does not have to be constant. Lift stations are needed in generally every gravity wastewater collection system. They're either not required or minimized for pressure sewer systems. And here again, a teaser for next week's webinar when we talk about the cost. We've looked at some data to see, what are the actual cost breakdown when you look at the total system. And lift stations are really not a consideration in the overall cost for pressure sewer systems compared to gravity sewer systems. Then you need, access to main lines. So you're going to have a manhole every 200 to 300 feet, 30 to 60 to 90 meters, and on bend. So you're going to have a lot of manholes in the systems. With a pressure sewer system, you're going to have some cleanups, but they can be minimized. And depending on how the system is laid out, you may not have that many at all. And one big thing, when I look at it from my experience, is with gravity sewer system, you always have conflicts with other buried utilities. If you're in an area with an existing utilities in it, the gravity sewer is going to be the lowest utility in the utility corridor. So you're going to have to work around the water line, the gas line, the fiber optic lines, or whatever else is buried underneath the soil. With the pressure sewer system, because you're buried just below the frost line, you're not only able to deviate horizontally, go higher, go lower, but you can also deviate vertically. So you can go around obstructions. You don't have to maintain a constant straight, constantly downward slope pipe. You can veer left, you can veer right, you can go up, you can go down. So you have that capability to avoid the conflicts with other buried utilities, as well as any other environmental concerns, such as wetlands or trees. Now, just quickly, as I mentioned earlier, I'm going to touch on sewer maintenance in each of the 3 webinars. This time, I'm only going to kind of introduce it as it is something that is required. When we look at sewer maintenance, it doesn't matter what kind of system you have, maintenance is required. And your general maintenance is going to be preventive, predictive, corrective, and if the first 3 don't work, that's when you run into the 4th one, which is emergency. So it's very important that when you're looking at gravity sewer versus pressure sewer, that you have the understanding that a well-planned and executed preventive maintenance program is key to keeping the gravity sewer system, or actually any sewer system, in good repair and operation. So you can't just install a gravity sewer system and forget about it. One of the things we'll hear all too often is they like gravity sewer system because once it's installed, yeah, it costs more in the beginning, but then it's free after that. And it's not. The rehabilitation, the TV inspection, the gravity sewer cleaning, the gravity sewer inspection, the gravity sewer rehabilitation repair is a multi-million, if not billion-dollar industry. So you do have to maintain that preventive and predictive maintenance, even on gravity sewer systems. And I'll go into, particularly when we talk about the life cycle cost analysis, a little bit more into that breakdown of sewer maintenance, how it applies to gravity sewer systems and pressure sewer systems. So where we are now, we'll leave a little less time for questions than we had hoped, but we'll get to them quickly. So this first part, quick overview, just show you a couple of the considerations that you want to look at when you're looking at wastewater collection system alternatives. Part 2, which is Thursday, and Rachel, correct me if I'm wrong, but I believe it's at 1 o'clock as well.
Yeah, Eastern Daylight Time. Yeah.
Yeah, and I'll make sure I know what time I'm supposed to be on by then. But yeah, that's we're gonna go into some of the basic design principles, and it's not going to be a design school because for gravity sewers or low pressure sewer system, that's a whole day thing just on itself on how you design a system. But I am going to touch on some of the things you want to look at, some of the ways that you design a gravity sewer system different than you design a pressure sewer system. Designing the pressure sewer system isn't more complicated, but you do want to look at things a little bit differently. And then next week on Tuesday, we'll have the overview of the life cycle cost systems, and then I'll get into a little more detail on the cost advantages, doing a life cycle cost analysis, and looking at the operation and maintenance costs as well as the capital cost to drive that alternative evaluation as you work through looking at your wastewater collection system alternatives.
Okay, Keith, thanks for that Excellent presentation. Keith has thrown up his contact details there, so jot those down. Of course, you'll receive all this information in a follow-up email. But that was so much rich content. Keith, thank you so much. So now we have an abbreviated Q&A session, but we have had some questions come in. If we don't get to yours, again, we'll answer them in a follow-up email. So Keith, we have a question that came in from Kristen. It's kind of a three-part series of questions, so you're going to need to pay attention. Regarding the individual grinder pump installation replacing a gravity system, has any study been performed on the increased energy needs due to the numerous pumps that would be needed to fully replace a gravity system? If so, were various size systems reviewed? And also, what is the life expectancy of the individual grinder pump? And also, you know, we have, as I mentioned before, we have Chris Nedwick on as well, so he may jump in at any time. So Keith, what do you think about that question from Kristen?
Good question. I'm going to work backwards. Life expectancy of the pump, you know, and I'm speaking strictly of the E1 semi-positive displacement pump, because there is a difference between semi-positive displacement and centrifugal in terms of life expectancy, because we always operate at the sweet point, whereas a centrifugal pump does operate on the extreme. So that's going to create some issues. But generally, we expect to see, based on a lot of studies that we've looked at, mean time between service of the pumps of about 10 years. And what we'll usually use for the life expectancy of an individual grinder pump would be about 20 years, 15 to 20 years. I know we have some pumps out there that have definitely exceeded the 20 years. So I would say, for planning purposes, if I were to do a lifetime cost analysis, I would look at I would account for replacing the pump or to build a short-lived asset reserve fund of about 15 to 20 years on the grinder pump. Now, going to the first part of the question, looking at the increased energy needs. No, I'm not aware of any study that has been performed, but if you're doing an evaluation of wastewater collection alternatives, it's something we could certainly help you with. With the E1 system, the power cost is very low. And one of the reasons I don't think there's been a study done is because usually that cost is borne by the homeowner. But generally, it's going to be less than $15, $20 a year. So if you have that at each property and you compare that to the major lift station that you have, one might expect that the power cost would be lower. I think one of the complications that you have when you look at these systems is, where do you draw the line? With gravity sewers, you have infiltration and inflow. So that infiltration and inflow is getting pumped to a system. Then you have the treatment of that infiltration and inflow at the treatment plant. So if you look at those costs, generally we would expect to see a lower cost overall, but I have not seen a study. Now, we do have one case study that I can refer you to on our YouTube page of Honey Path, South Carolina. We also have some, I think we got some case studies there on Athens, Tennessee, where these are two communities that did replace their failing gravity sewer systems with E1 low pressure sewer systems. And one of the drivers and one of the advantages that they did see for that was a reduction in the overall operation cost.
Okay, thanks, Keith. A question here from Edward. What are some common maintenance issues related to the E1 system? Can there be any plugging of the system or catastrophic failures of the pump itself? And is there any access needed or typically designed for the collector portion of a pressure pipe system?
Yeah, well, the E1, one of the nice things about the E1 system is it was designed, as I mentioned, by a group of engineers at General Electric. These were appliance guys. So they kind of had this mentality of, an appliance, really no different in terms of service from your home washing machine or your refrigerator. But it is a piece of mechanical equipment. So I can't say that there would never be any catastrophic failure of a pump. We don't expect it to happen, and it doesn't happen that often, but it is a mechanical equipment. So you do have some maintenance that you have to look at. I forget I went on a tangent in my head, Rachel. What was the first part of the question?
Okay, hold on. The first part is what are some common maintenance?
Oh, okay, thank you. Yes, I knew it was an easy one. Yeah, so the nice thing with the E1 system is it's almost predictable on where we're going to see the maintenance. You have the rotor and your stator. And the most common, and Chris, please correct me if I'm wrong, but don't tell anyone I was wrong. The most common repair is the stator, that it will get worn down over time. It is something that is predictable. You'll notice some change in performance if you have some of our analytical features in there. So when we do see a mechanical problem, it's usually a very common something that the operators have seen before. That makes for a very quick repair. And in terms of the collection system, you really don't, we would typically recommend that you have some clean outs where you might be able to do some flushing, but generally you don't need to maintain the collector portion of the pressure pipe. With the E1 system, because it has that flat curve, if there are any obstructions within the system, it will generally push those along, because you're not going to move to low flow or high head, low flow situation that you would with a centrifugal pump.
Okay, thanks. And this will be our final question, I believe. And like I said, we'll follow up an email with your other answers there. So can pressure sewer be used with other types of collection systems?
Yes, absolutely. One of the well, I don't know if it's common. Whenever we do see it, is a gravity sewer system that is being expanded. And as I said, it's hard to expand a gravity sewer system with more gravity sewer system if that system wasn't designed for that expansion. But with the pressure sewer system, you could have a sub-basin that ties directly into an existing gravity sewer system. Discharge into a manhole or discharge into a lift station. We also have some installations, and I wouldn't see it everywhere, but we have for a basement flooding application up in Oakland County, Michigan, where they have individual grinder pumps that discharge into the gravity sewer that's in the main, because that gravity sewer becomes surcharged at times, so they use it to prevent backflow into the house. So I would say the only place you can't combine a E1 sewer system with another type of system is you really can't tie it into a vacuum sewer system. But you can tie it into other particular gravity sewer systems without any problem.
Great, thanks, Keith. So it looks like we're just about, in fact, we're over time here. So on behalf of all of us at E1, we thank you for joining today's session and look forward to seeing you this coming Thursday, which is the 25th of June at 1 p.m. Eastern Daylight Time for part 2 in this series, which is Basic System Design Principles. Until then, take good care.